Okay. So as I mentioned, we're going to look at continue the discussion on the topic on the introduction to systems engineering, and my goal is again for you to have a good understanding of this subject in terms of what we are looking for within systems engineering and how it is different from the other disciplines in engineering. So these are the references that I'm going to be using for this particular lecture. So the ones in red, one of them is your course textbook. The other one is the textbook on the engineering design of systems by Hoboken. So this is one quote from Aristotle, very old quote, and it says the whole is more than the sum of its parts. And it basically summarizes what we are trying to achieve within systems engineering. We are not, as I mentioned last week, we are not just focusing on the specifics. We are trying to see how all these components can work together to achieve a common goal. And how can we devise strategies for interfaces that are effective in terms of if you put together a system that the overall system will perform as expected. So the idea here again with this quote is that you see our goal within systems engineering. We're focusing more on the whole than in the particularities of different disciplines. We are focusing on how everything interacts. So our main goal, which is the whole system, perform as expected. So we went through the first 4 bullets of this slide already. Today we're going to continue our discussion and we're going to focus on the systems engineering point of view, which is SE point view. And then we're going to talk about systems engineering as a profession. So how is this different? How is it similar to other professions? And finally, we are going to conclude our lecture with the power of systems engineering. Why is this powerful? Why is this concept good for you as a professional? Okay, so let's start with the system engineering point of view. As I mentioned already, we are focusing on the overall performance of the system, not on their individual components. So it makes the central objective the systems as a whole and the success of its mission. So again, we are trying to put together something that is complex, that is engineered, right? We are not dealing with living organisms. We're dealing with engineering systems that are complex, that requires multiple disciplines to collaborate in a way so we can achieve our goal, our success. Takes a big picture or holistic view of large problems and their proposed technological solutions. So again, we are not just looking at, okay, I want to save money. I also want to look at the big picture in terms of how is this solution going to affect my company in the next 5, 10 years? How is this solution implementation is going to have an effect on the society? How is this solution will have an effect on the graduation rate at Texas State University, for instance? So we are focusing on the big picture. And this is again one of the figures that I like to show. It's just a representation of what will happen if we just focus on individual things instead of the overall perspective or the system as a whole. So if we focus on specific disciplines, even though we are trying to achieve the same mission or the same goal, we are going to be looking at the problem solution from our own perspective, from our own knowledge. But that's not what we're trying to achieve with systems engineering. What we're trying to achieve is how can we combine all this knowledge so we can come with the best or the most balanced solution or system to address our problem. So what do we mean by the best? Okay, so if you have already taken operation research, i.e. 3340, we talk about what is the optimal solution. And do you remember what an optimal solution is? What is an optimal solution? Any ideas? How many of you have taken 3340? So when we talk about optimal, what does that mean? You can guess. It's okay.
Most profitable or something that uses most resources.
Yeah. It has some along those lines, something along those lines. So we can have a group of solutions for the same problem, right? The optimal solution is the best on that group, meaning that there's no, if you have 3 possible solutions that will satisfy, let's say, the budget, the optimal solution is the one that is going to give you the best use of that budget, meaning that you're going to spend less money, but you're going to still get the same results, right? So the optimal solution is looking at the best solution among a group of solutions. But in systems engineering, we are not looking for that, okay? We are looking for the best in the name of the good. Systems engineering is the art of the good enough. Okay, so what I'm trying to say here is we are not looking for the optimal. We're looking for a solution that will help us solve the problem. So systems engineering seeks the best possible system, which often not the one that provides the best performance. Okay, so when we say the good enough, basically we are dealing with very complex situations, right? So we want to find the right balance among different things. And I mentioned already 3 areas that are important, let's say schedule, cost, and performance. So which solution will give you the best balance among those 3 objectives? Systems engineering views performance as only one of the several critical attributes. Okay, so some of the things that we need to consider: affordability, right? What if the best performance, you end up spending a lot of money, right? And you don't have that money. So affordability is important. Timely availability to the user. So maybe getting you the optimal system is going to take too long. So you are not going to have that system available when you need it. Easy of maintenance. This is very important. So it's not just building the system, but you have to make it operational for a long period of time. So maintenance becomes a big problem if you don't manage it appropriately. Adherence to a agreed upon development schedule. So systems engineering seeks the best balance of the critical attributes. Okay, so we are not looking for the optimal solution. We are looking for the best balance among different or critical attributes. And some of them are listed here. Any questions? So I like figures, and I think your textbook does a good job trying to show some of the ideas with these graphs. So I'm putting them into the slide. So this is the law of the diminishing returns. What this means is we have the cost versus the performance, and we are going to have some thresholds that we want to meet. And say this is the performance. We want our performance to be within these bounds, right? So what this is trying to show you is at the beginning, every solution is going to cost you some money or some resources. So the cost is represented here. This curve is showing you that if you want to achieve that minimum performance, you're going to have to put more resources, right? So it's going to cost you more. But at some point, this is a very steep curve at this point, but at some point, once you reach that threshold, that performance is not going to improve as much, but the cost is going to keep increasing. Right? So what we are trying to show here is that if you're looking for that good enough solution, you don't have to go and spend all this money. Because if you're within that threshold, the minimum acceptance, and you can spend this amount of money, you're going to be saving some resources, and you still meet the purpose of the system. Right? So the other thing that we're trying to show here is that at some point, by the law of the diminishing returns, you are not going to see too much improvement. Like when you get to this part, you don't get as much improvement on the performance of your system, even though you're putting that much or those resources, or you're spending more resources on it. Okay, so so achieving that performance again doesn't necessarily mean that you have to go the whole way to the 100%. We can find that good spot in which we have the right balance of the performance, and you don't end up spending that much of your resources. So here's another curve that combines the cost versus the performance and cost. So again, it's kind of representing the same idea, but now we have a combination of performance and cost. And this is showing you a curve of that ratio versus the cost. And you will see that the best solution, which is the minimum acceptable performance, will happen at this top, at the top of this curve. At this point, that ratio is going to start decreasing. So if you were to find an optimal solution for this curve, this will be a maximization problem. That would be this point right here. That's where you achieve the highest performance of this ratio. And again, that will not increase, that ratio of performance cost will not increase anymore at this point. At that point, it will go down, even though you're putting more resources into your solution. Okay? So that being said, I want you to look at this case study in which systems engineering plays a major role. And the thing about this case study is that it is a case study that went wrong. Okay, and people learn some lessons based on that, on the wrong things that they did. And this is called the Hoover Space Telescope. It's a project that was started by NASA in 1977. And the Hubble was ready to be launched in 1986, so about 10 years later. Challenger delayed the launch by 4 years. And this is a telescope that was looking for better images of the space and the Earth, right? So it would eliminate the atmospheric effects that blur images seen on Earth. So the idea is to build this telescope, put it up into space, and that telescope will be able to get you better pictures to do research. So the project started, the idea came from this person in 1946. The National Academy of Science proposed launching a telescope into space in 1972. And then in 1977, NASA began the Hubble Space Telescope. It was launched in 1986. So you see it's about 40 years difference between the idea and the actual launch of the system. And something happened at this point. So I want you to look at the case study. I'm going to show you where that is in a second. You're going to be working in groups of 2. Like we have 6 today. If you can just build 3 teams of 2. And you're going to be answering these questions. What was the goal of this telescope called the Hubble? What was the overall estimate cost of the project? What was the problem with the Hubble? And how could this problem have been avoided? Do you think the cost for preventing the problem was justified? And so let me show you where that is located.